Do you notice that our computers are faster up here? You think so? Yeah, especially when it updates. When it says, please wait, it feels like we wait less. Yeah, I agree. We definitely wait less. All right, enough of the bad puns. Let's learn about some gravitational force. Okay, so in the previous video, we talked about gravitational fields, which we drew with these lines to represent a gravitational field, which is an invisible kind of force field, because if we place a mass there, it's going to undergo a force. And yesterday, or in the last lesson, we were all talking about how to calculate the strength of that field. But now we're going to say when we do put a mass there, how are we going to be able to calculate that pull of attraction that's between two masses and calculate that amount of gravitational force? And that formula for field strength, we're not actually going to throw out. We're actually going to use it and just barely change it. So this was the gravitational field strength formula. And this is the gravitational force formula that we saw actually from an earlier chapter. We use this to calculate the gravitational force on the surface of Earth. We just did mass times g, which we use as 9.81. But now we know that that g is actually just the field strength. 9.81 newtons per kilogram or meters per second squared describes the field strength on the surface of Earth. So now when we go into outer space or in other places and we have a new field strength, we calculate it with that formula. G is gms over r squared. So we're just going to combine these two. Say the force of gravity is your mass times lowercase g is what we used up there. But now we're going to replace that with gms over r squared. Move the m to the middle and we get the formula that's usually on your data sheet. Fg is equal to gm1 m2 over r squared. And that's it. Very similar to what we had for gravitational field strength, just throwing in the mass of that other thing that we place in the field. So let's try some questions with this. Okay, our first one, what gravitational force does the Earth exert on the moon? Okay, so it's asking for gravitational force, not on the surface of Earth, so we're going to have to use this bigger formula for places further away from Earth. So at the position of the moon, we'll use Fg is equal to g m1, m2. That's just the two masses. Doesn't matter the order you put them in, but we'll put the mass of the moon and the mass of the Earth divided by the radius, reminding that's the distance between the two objects. So we'll throw in first our capital G. That's the same constant we saw before from gravitational field strength. The mass of the Earth, pretty heavy, 5.97 times 10 to the 24. And the mass of the moon, a little bit smaller, actually quite a bit smaller there, 7.35 times 10 to the 22. That's not necessarily a hard operation, just multiplying these together, but there are some pretty big numbers. So we've got to make sure we put in the calculator well. We'll go over that in just a minute. Next, the radius, again, from the center of the center here, we're going from the moon to the Earth. And this is described usually on a data sheet or a formula sheet that you'll have as the moon's orbital radius, because the moon's orbiting around the Earth. How far apart they are in that orbit is the moon's orbital radius, and it's 3.84 times 10 to the 8 meters. Also, don't forget to square that number. Let's put that in a calculator, see what we get. Let's bring up the calculator here. And so I'm going to start in brackets with 6.67, but instead of going times 10 to the exponent and hitting negative 11, to replace times 10 to the exponent, I'm going to hit second comma. That's common for lots of TI calculators. And it brings up this E. It might be a different button on your calculator, but it brings up this little E that represents times 10 to the exponent. And what's nice about this is it treats it as just one number, 6.67 times 10 to the negative 11, not as an operation of 6.67 multiplied by times 10 to the negative 11. The E keeps it all as one value. I like to put brackets around it still just to keep things clean. That should actually help it keep it as one number. The same thing for 5.97 e to the 24 and 7.35 e to the 22. Now, because we've got a lot of numbers here, I would press equals and see what we get for the numerator. Get our value for that old top number, and then we'll divide by the denominator. So get our answer, now divide by 3.84 times 10 to the 8. Make sure that's in brackets because we need to square that number. We don't want to square just the 8, square that number in brackets. And we get a number of 1.98 times 10 to the 20 newtons. Now, before we leave this scenario, let's try flipping it. That's the force that the Earth's going to pull on the moon with. But what about the force that the moon pulls the Earth with? Let's take a look at that. What gravitational force does the moon exert on the Earth? Okay, so just change it to moon pulling on Earth. Now we're going to start with that same formula for gravitational force. G is going to be the same, so let's put in 6.67 times 10 to the negative 11. And then the two masses. So now moon and Earth, so I'm going to put in the mass of the Earth and the moon, and the distance is also the same between the two. And we get the exact same answer as we had for the force that the Earth pulled on the moon. So this is saying the moon and the Earth are pulling on each other equally. That probably doesn't make intuitive sense because it definitely seems like the Earth is heavier and the moon is orbiting around the Earth. So it would make sense to think that the Earth was pulling on the moon more. However, what this is actually kind of going based off of is Newton's third law. If the Earth is going to pull on the moon's going to pull on the Earth with an equal and opposite force. Okay, well, we have a reason for that, but still doesn't really seem to make sense. Let's take another look at an example. Let's imagine this scenario that is not at all to scale, but there's a person on the surface of Earth, like we all are on the surface of Earth right now, and they're going to jump up and gravity's going to pull them back down. Just like if you were to jump up and gravity's going to pull you down. Okay, so here's the person's going to jump up. Okay, and they're up in the air. The reason they're going to fall back down is because the Earth's going to apply a gravitational force down on that person. Now, we said Newton's law, and really our force of gravity formula, says you will pull with an equal and opposite force, pulling the ground up towards you. Now, so when I put that there, you might think, does that mean the Earth actually comes up to me? Well, not really. Why doesn't the Earth come up to you? You go down to the Earth. Because of the relative masses here. We said if they apply an equal and opposite force, let's just say 700 newtons. You jump up, and then your mass times gravity, it pulls you down with 700 newtons. It pulls you down with 700 newtons. The Earth gets pulled up by you by 700 newtons as well. That 700 newtons, if we divide by the mass, is going to be a significant acceleration. We divide by the mass, 700 divided by 70 is approximately 10, so we'll say like 9.81. You're going to get significantly accelerated down. However, if we switch this to the Earth's mass, we go to 700 newtons applied to the Earth, but divided by Earth's mass right here, the Earth's mass is huge. So 700 newtons applied to the huge mass of Earth doesn't really affect it all. So the acceleration of Earth coming up to you is like extremely tiny. That's why the person's going to accelerate down and the Earth isn't really going to move up. Even though you have an equal and opposite force, it's going to affect the lower mass way more, which is the same reason why when the moon and the Earth are pulling equally on each other, the moon's much lighter. So it's going to be whipping around the Earth. They're just going to wobble maybe a little bit because of it, but it's not going to be orbiting around the moon. Okay, so I hope that helps you understand that and just plugging in. Let's try a bit of a harder example here. This one's going to say a satellite experiences a force of 300 newtons at 5.1 times 10 to the 6 meters above the surface of Mars. What is the mass of the satellite? Okay, here we have our satellite going around Mars, and we're trying to figure out the mass of that satellite. Since it gave me information about gravitational force, let's start with that formula for gravitational force and rearrange for M2. So I kind of put with colors here. This one is the mass of Mars. This one is the mass of the satellite that I'm trying to solve for. Again, they're just both masses, but let's imagine that's our setup. We're going to take our R and multiply it over to Fg, divide by our gravitational constant, divide by the mass of Mars, and we should end up getting a formula for the mass of the satellite. Plugging in my numbers, I have 300 newtons, and then I have the radius. We saw 5.1 times 10 to the 6 meters. There it is, going in there. Gravitational constant, and then the mass of Mars. However, unfortunately, if you plug that in your calculator, you're going to get the wrong answer on a test. Why is that going to give you the wrong answer? It looks almost entirely right. We really have to notice that this says above the surface of Mars. That's not, keeps going back there, the distance from the center of Mars to the satellite, which is what the radius is measured as. For gravitational field strength and gravitational force, you have to go from center to center for each object. So we can see in that picture, the green line there is the distance to the surface. We need to include that blue section to get the total distance from the center of the satellite to the center of Mars. So what's the distance of that blue one? That's the equatorial radius of Mars, and that's usually on your data sheet as well. So we're going to have to plug that in there. There we go. We got 3.39 times 10 to the 6 plus the height above the surface. We can see on the picture too, the green and the blue sections add up to that total radius. And at that point, we're good to plug in. Let's go into our calculator. 300 times, I'm going to put this in brackets, 3.1 e, or times 10 to the 6, plus 3.39 e to the 6 as well. Bracket those two numbers, square it, and get our answer at this point. Get your numerator solved. Now we're going to divide by the denominator. There's a multiplication going on in the denominator, so I have to put double brackets around this, so it divides by all of it. So double bracket 6.67 e to the 11, negative 11, and then my 6.3923, double bracket at the end, and we should get our answer here. And I'm going to put that on the slide as 5.0 kilograms, not 5.0, 507 kilograms for the mass of our satellite. Okay, let's finish off the video with one more example. Examples that I like to call proportional reasoning questions. This is where we have a force between some planets, but then we're going to maybe change the planet to make it bigger or smaller, and then go closer or farther away and see how it's going to affect the result. So a question might look like this. It says the gravitational force between a planet and a moon is 5.0 times 10 to the 7 newtons. If the planet was 3 times larger and the moon was 2 times smaller, and the distance between them is 1.5 times further away, what would the new gravitational force be? These can be pretty intimidating to solve because when you think of the formula g m1 m2 over r squared, I don't know the masses of either of these, and I don't know the radius. All I have is these proportions, which is why I call it proportional reasoning question. So look what we know. We know that the force between the original planet and moon is 5 times 10 to the 7. I don't know the masses of the radius, but I'm going to put in how you would get that number is with the formula for gravitational force, gm1 m2 over r squared. So all that equals 5 times 10 to the 7. So what I would do next is write that formula again and kind of space out your numbers a bit like this. I said space them out because now we're going to put in how much they've changed by. So I have my original mass, but now it's going to be 3 times larger for the planet. And I have my original mass for the moon, but that's going to be 2 times smaller, or half as big. So I put in 0.5. And the radius 1.5 times larger. Doesn't seem like we've done too much yet, but let's take those factors and just move them to the front. So instead of like g times 3 times m, let's go 3 times g times m. We're just going to change the order, but the order of multiplication doesn't matter. So let's move those factors to the front. So I have 3 times half times g times m1 times m2 over 1.5. The 1.5 is actually probably the trickiest part. If I want to isolate that number, that factor, it's 1.5r, and that is squared. So if I take my pen here, it's not just the r that is squared, it's the 1.5r that is squared. So if I want to isolate the 1.5, it's actually r squared and 1.5 squared. So let's throw the square on there, and now what we've done is I've isolated all the factors to the front. So I have 3 times half over 1.5 squared, and all that is kind of multiplied by gm1 m2 over r squared. It seems a bit confusing, so let's simplify this. Let's take all my factors at the front here and reduce that. So 3 times a half divided by 1.5 squared gives me 0.6 repeating. It's a whole bunch of 6s in the calculator there. So now I've got 0.6 times gm1 m2 over r squared. And at this point you might be thinking, well, I still don't know m1, m2, or r squared. I'm missing 3 pieces of information. How am I expected to solve it from here? You're actually just about done because you don't know what m1, m2, or r is, but I do know what all of them together are, and that's equal to 5 times 10 to the 7. So I can plug this number in for that formula, and now I just have 0.6 times my original amount. I multiply that, we get our final answer of 3.3 repeating times 10 to the 7 newtons. Okay, so that's all we have for this video. Thank you so much for watching. I hope that helps you to understand gravitational force and how to apply it to these 3 questions. On this channel, we do an entire playlist of lessons on high school physics and science courses, and other videos linked here. So thank you so much for watching, and I will see you in the next video.